Hi everyone, in this video we are going to discuss about electrical analogies of mechanical translational system with example problem. Here this is the given mechanical rotational system for which we have to write the differential equation and we have to draw the force, voltage and force current electrical analogous circuit and verify by writing mesh and node equations. If you see this particular system, we have two nodes, one at M1, another at M2. Therefore, we have to draw a free body diagram at M1 and free body diagram at M2. Let's see the free body diagram at M1. We see that M1 we are having an applied force. So it is F of t is given. This M1, B1, K1 and B12 will provide an opposing forces which are represented here. Using Newton's second law, we can write a force balance equation, that is Fm1 plus Fb1 plus Fb12 plus Fk1 equal to applied force is F of t. Fm1 is m1 d square x1 by dt square. B1 it is Fb1 it is b1 dx1 by dt. B12 it is available between the two nodes. So two nodes means two masses. So B12 into d by dt x1 minus x2. Similarly, the spring K1 is between the two masses. So it is K1 into x1 minus x2 which is equal to F of t. This is equation number 1. Let's see the free body diagram at M2. We take an M2. There is no applied force directly to this M2. That is why we don't have any outgoing arrow. What are the opposing forces? M2 will induce opposing force. We have K2, B2 will introduce opposing force, K2 and B2. This side K1 and B12 will provide an opposing force. Using Newton's second law, we can write a force balance equation. Here only opposing forces which are equal to 0 since we don't have an applied force. We get an equation number 2. In this particular step, we are going to replace the displacement by velocities. So we will be replacing the displacement by velocities in the equation 1 and 2. All the displacements we are representing in terms of velocity. It is an acceleration d square x by dt square. It is the first derivative of velocity. Dx by dt is nothing but it is a velocity. X is integral v dt. We are going to replace these terms in the equation 1 and 2. We will get the equation 3 and 4. If you see here, in example M1, d square x1 by dt square, which means it is dv1 by dt. Likewise, we are replacing all the elements. If you take a K2 x2, it is K2 integral v2 into dt which is equal to 0. This particular step, we are replacing the displacements in terms of the velocity. Let's see the force voltage analogous circuit. If you see this particular given mechanical system, we have two nodes. Therefore, in electrical system, we have two meshes. And see here we are having two meshes. In mechanical system, the input is f of t, which is replaced by voltage E of t because it is a force voltage analogy. Velocity v1 is replaced by current I1. Velocity v2 is replaced by current I2. Mass is equivalent to inductor. Dash part, it is equivalent to resistor. And the spring is equivalent to capacitor. Usually we will get 1 by C1 and 1 by C2. So for easy understanding, I am writing it as C1 and C2. Now, if you consider the mass 1, we are having an applied force. So in this particular mesh 1, we are having an voltage source. And M1, which is equivalent to L1, B1, which is equivalent to R1, and K1 and B12 are available between the two nodes. Therefore, these two elements should appear as a common element between two meshes. And in force voltage analogy, the common element should be connected in series. In case of a force current analogy, these elements should be connected in parallel. We will see later. This B12 is nothing but R12. K1 is nothing but C1. Now we are coming to this particular node M2. It is represented by L2. Why we don't have any voltage source? Because we are not having a separate applied force at this particular node. And this B2 is represented by R2 and K2 is represented by C2. This is how you have to draw a force voltage electrical analogous circuit. Now you consider this force voltage electrical analogous circuit. For this we are going to write the mesh equation with the help of the KVL. You see, whatever we are having the elements in the first mesh, I have written the voltage across each element. Voltage across inductor is L into di by dt. Voltage across resistor is IR. Voltage across the capacitor 1 by C integral I dt. Since this capacitor C1 is common between the two meshes, so it is I1 minus I2. We have to add all voltage drops which is equal to the source voltage, it is E of t. In the mesh 2 we don't have any applied voltage, or I can say there is no voltage source, so it is 0, and you have to add all the voltages across individual elements. It is summed up. This is equation number 5 and 6. Now I have written the equation number 5 and 6 from the force voltage electrical analogous circuit, and the equation 3 and 4 basically it is a differential equations governing the mechanical system. If you compare the equation 3 with 5, it is more or less it is similar. All the elements which are similar. Similarly, if you take equation number 4 and equation number 6, these two elements or these two equations are similar. Means from this slide it is observed that mesh equations are similar to the differential equations governing the mechanical system. Next, let's see how to draw a force current analogous circuit. The given mechanical system has two nodes. Therefore, in force current analogous circuit, we will have a 2 nodes. And the input force is represented or replaced by means of a current source. Velocity is represented by means of an voltage. Velocity V2 is represented by means of the voltage V2. And the mass is nothing but the capacitors. The spring K1, K2 are nothing but actually 1 by L1 and L2. For your easy understanding, I am giving L1 and L2. And this dash part is equivalent to resistor. We have to write 1 by R1, 1 by R2, 1 by R12. For simplicity, I am giving it is R1, R2, R12. Let's see how to draw a force current analogous circuit. For the mass 1, we are having an applied force. That is why we are having a current source, I of t. This mass is represented by the capacitor. In case of a force current analogous circuit, all the elements to be connected in a parallel. In force voltage analogous circuit, all the elements should be connected in a series. That is why C1 appears in a parallel, and this B1 is nothing but R1. We have a node 1 here, and K1 and B12 appears as a common element between two nodes. Similarly, in electrical circuit also, it should be a common element between the node V1 and V2. B12 is nothing but R12. K1 is nothing but L1. Next, I am representing this V2 node. M2 is represented by C2. B2 is represented by R2. K2 is represented by L2. This is how we have to draw the force current electrical analogous circuit. Now, for this force current electrical analogous circuit, we are going to write the mesh equation using KCL. So, you take V1 is a node for which we are having a current I of t. This is actually an force voltage analogous circuits. How we achieved this one in the sense, we are considering a previous one, that is a force current analogous circuit. So from this V1 and V2, we are going to draw what is the current through each and individual elements, and we are applying a KCL. Sum of incoming current is equal to sum of outgoing current. In the first node, we will have this incoming current as I of t. Whereas in the second node V2, if you consider, there is no separate incoming current, so it is 0. All the outgoing currents are added. These are the equations 7 and 8. If you see the equation 3 and 7, it is similar, and equation 4 and 8, it is similar. Means that the node basis equation are similar to the differential equations governing the mechanical system. This is how we have to obtain the force voltage and force current electrical analogous circuit. These are the references. Thank you.